Yes, good morning. Everybody, can you listen to me? Please raise your hand. Yes, everybody, good morning. As I told sir, today we will close little early, but tomorrow I will take from 7 to 1. Okay, 7 to 1 or even little early if necessary. I will declare that today. Okay, what do you say? Is everyone okay? So tomorrow schedule will be big, and again Sunday also I will take big. So we will complete, sir. Definitely, I am planning to complete syllabus as early as possible. Okay. Chalo, now in that regard, everyone. Yes, I want everyone to concentrate. See what we did last class. Quick review. Okay. Quick review of what we did last class. Okay. So last class, yes, we were doing inductor capacitor chapter, and this yesterday we even entered capacitor problems. But in that inductor capacitor, this was an ideal case. What is that? Yes, I told that there are two ideal inductors. Initially, the switches are at position A and A dash. They become independent loops. Okay, then steady state current, flux linkage, and energy. Then both are simultaneously moved to position B and B dash. Okay, again, steady state currents, flux linkages, and energy, and verify law of conservation of flux and law of conservation of energy. So this is such an ideal case that it is not easy to explain, but mathematics is there, and the real secret proof is coming from Laplace transform. Okay, that is why such ideal concepts, if you understand later, practical things are more easy. In fact, so in that regard, yes, this is also assume that the switches are having no losses. Okay, it's also assumed that switches doesn't have any losses. Okay, and there is no power loss in transit or energy loss during transit. So before change, we got everything: flux linkage, energy, everything, and total flux linkage and total energy. After change, yes, that is what, sir. Here, these are lossless inductors and lossless wire. The energy stored in inductors in magnetic form continue to flow forever. As that energy is not coming out, currents continuously flow, which is how much current we got. Yes, that current is 5 amperes. But this answer we got by taking law of conservation of flux only, and the proof secret came from Laplace transform. What about law of conservation of energy? It is not that we are violating law of conservation of energy, but we are justifying saying that some part of the energy from the previous state is utilized to redistribute the flux to maintain constant equal current. That is a very, very interesting statement I give. Then we came to time variance problem. Yes, this is the first time variance problem from the given current function, voltage function, then power function, okay, then energy function, okay, then all these bits period. That means we understood inductor how it is working. Now you give me any time varying signal, I will explain like that. Then even for such extreme case, yes, impulse voltages, okay. Then in such case, yes, now this is passive notation, this is KCL demonstration, okay. Then this is practical inductor also, okay. So all these things we studied, including state variable concepts, okay now. Then we started capacitors, capacitor reduction techniques we started, okay. So let us continue from there, okay. Let us continue from there. Okay, now I'm continuing, sir. Everyone, yes, you should understand this. Now, this is an IES objective. Quickly, sir. Okay, convert into delta. This is the question. Convert this into delta. Node 1, node 2, node 3, 1 farad, 2 farad, 3 farad. Okay, convert this into delta. Okay, convert this into delta. Okay, then this is a gate question. Gate question. Determine the input capacitance. Determine the input loop capacitance. Determine the input loop capacitance. Okay, determine the input loop. This is 1 kilo ohm. This is 2 kilo ohm. This is 3 kilo ohm. This is 2 microfarad. This is 200 microfarad. And this is current I, and there is a dependent current source. Okay. Yes, it is 24I. Okay. This is the input loop. He mentioned in the question itself, this is the input loop. Like that he wrote in the exam also. Okay, shall I do these two problems? First question is convert this star into delta. Second question, determine the input loop capacitance. See, very interesting question. Determine the input loop capacitance. Shall I 1 minute, everybody, quick. Determine the input loop capacitance. Only 1 minute, sir. Convert this star into delta and determine the input loop capacitance. Yes, answers. Yes, over time up. Now listen, sir. See, star delta delta star transformations in capacitor is same like resistor, but reciprocate every term, sir. See, now let us say this is something like C1. Let us say C or CX. But what we write in register, this will be this plus this into this by opposite. But here reciprocate every term, including the left hand side. So what I will write now, this 1 by Cx is, okay, this plus this, that is 1 by 1 plus 1 by 2 plus this into this 1 by 1 into 1 by 2 by opposite 1 by 3, that is 3 by 2 plus 3 by 2 is 3. So if 1 by Cx is 3, Cx is 1 by 3 farad. So you will get this as, yes, you will get this as 1 by 3 farad. Then you do this, sir. I'm sure. Yes, you do this also. You will get this as 1 farad. And then finally you do this delta branch here also. You will get this as half farad. Okay. So same like register formula, but reciprocate every term, including the left hand side. Don't forget that. That is 1 by Cx is 1 by 1 plus 1 by 2 plus 1 by 1 into 1 by 2 whole by 1 by 3. So now look at the next question. Determine the input loop capacitance. See, first of all, in this problem, not like the problems like we did yesterday, like here you see what is total capacitance. Okay, what is capacitance C total, like that he did not ask. Why he did not ask like that? Because we cannot lump the two capacitors together. There are resistors in between. So here we cannot lump the capacitors together. Okay, so instead is asking determine the loop capacitance. Loop capacitance is a capacitance offered while writing the loop KVL. Loop capacitance is a capacitance offered while writing the loop KVL. So please understand, sir. Please understand loop capacitance. It is a capacitance offered while writing the loop KVL. Okay. Yes, loop capacitance. So because here capacitors cannot be lumped into single element, we cannot ask total capacitance. Instead, loop capacitance. So for that, what I will do KVL, because he is asking loop capacitance. Please understand, because he is asking loop capacitance, I will write a KVL. I will write a KVL. But suppose if it is junction capacitance KCL, loop capacitance KVL. So let us write a KVL. Now let us assume there is a time varying voltage Vs of t. because this is capacitor problem, na, sir. I will assume some time varying voltage, which is allowing this time varying current I. Now this I will flow here, and current dependent current source, this 24I also will flow here. Okay, this I will flow here, 24I will here. KCL, if you apply, this total current will be 25I. Yes or no? So now I am writing the loop KVL. So if you write a KVL, minus V of t or Vs of t, okay, plus IR, I into R, that is 1K plus 2K, 3K plus 1 by C, 1 by C, okay, integral I dt, 25I dt equal to 0. Okay, minus Vs of t plus IR, I into 3K plus 1 by C integral I dt equal to 0. Now from that I can write, yes, from that I can write, this Vs of t is equal to, this is I into 3000, okay, I into 3000 plus, if you remove this 25 ones are 25 8s are see 25 ones are 21 by 8 micro integral I dt. So now this is in standard Ohm's law form. What is this standard Ohm's law form? Like V equal to IR plus 1 by C integral I dt. So from that I will say the C loop is 8 microfarad. Loop capacitance is a capacitance offered while writing the loop KVL. There is a meaning here. There is a very interesting meaning, Nasar. Okay. So, what is the loop resistance? What is the input loop resistance? If anyone asks me what is the input loop resistance, that is 3000 ohms. What is the input loop capacitance? 8 micro. What is the input loop time constant? Because here both capacitors cannot be lumped, Nasar. We cannot say total capacitance, but interesting concept called loop capacitance. Okay. So now here input loop time constant tau is RC, Nasar. R is 3K. C is how much? 8 micro. So total 24 microseconds it becomes like that. 24 milliseconds because it is 3 kilo 8 micro, it becomes 24 milliseconds like that. So such concepts are important, sir. Okay, because here we cannot lump the, yes, we cannot lump the capacitors together. There is a meaning here. Okay, there is a meaning. Okay, so I'm going further. Now this is a direct gate bit. Everyone should do immediately. Yes, what is CXY? This was given for ECE in 2006. What is CXY? All are capacitors. What is CXY? Okay, this is 10 microfarad, 20 microfarad, 30 microfarad, 40 microfarad, and 50 microfarad. Chalo, quick, everybody, 1 minute. What is CXY? Quick, sir, everybody should do this immediately. What is CXY? What is CXY? 1 minute only. Now, see, this is an unbalanced bridge. Yes, this is an unbalanced bridge, sir. Here also convert because the bridge is not balanced. You have to consider even the cross arm or central arm, which is 30 microfarad. So convert one of the delta into star and do. Like here also, suppose I convert this into delta. Okay, 2 star. Yeah, delta 2 star. Let us say this is some Cx. But what I will write, reciprocate every term including the left hand side. So this 1 by Cx is this into this. Okay. Now also take magnitude scaling. See here in this network, take magnitude scaling. Okay. Scaling by dividing with 10 microfarad. Take magnitude scaling by dividing with 10 micro. Then becomes 1, 2, 3, 4, 5 micro, 5 farads. So then this in register, what we have done, product of these two adjacent by somebody have to reciprocate. 1 by Cx is this into this. That is 1 by 1 into 1 by 2. Because I took 10 microfarad common na, by divided na, by sum. 1 by 1 plus 1 by 2 plus 1 by 3. Okay, so this is 1 by 2. By if I take LCM 6, this is 11 by 6. 2 ones are, 2 threes are. So it is 3 by 11. So if 1 by 6 is 3 by 11, Cx is 11 by 3. So finally we get this as 11 by 3 farad. This you will get it as 11 farad. And this you will get it as 11 by 2 farad. Then I will further reduce. Now after doing so, now what the network becomes, the network further becomes like this. Okay, network further becomes like this. After converting that, yeah, delta to star, it becomes something like this. This is Y and this is X. So this is 11 by 3 farad, 11 farad, 11 by 2 farad, and this is 5 farad, and this is 4. Because I took magnitude scaling now again simplify. You will get this Cxy as, okay, you simplify, sir, you will get this as 2.239 into 10 microfarad. This 10 microfarad, why? Because we did so. This answer finally will be 22.39 microfarad. Okay, this will be the answer. You do it now. Series parallel answer. So first I divided by magnitude of 10 micro, and then I converted one of the delta into star because it is an unbalanced bridge. And then after getting that, yes, series parallel combination, then again I multiplied, yes, with the scaling factor what we divided again back with 10 micro. I multiplied. Now the answer is 22.39. Now I'm giving another interesting. Here's is an IES question. IES question objective. If if equivalent, yes, if equivalent capacitance, okay, between two opposite electrodes, okay, opposite electrodes is C farads, farads, then then total CAB is equal to dash. If equivalent capacitance between two opposite electrodes is C farads, then total CAB is dash. Okay, chalo, 1 minute. If equivalent capacitance between two opposite electrodes is C farads, then total CAB is dash. Chalo, 1 minute, everybody, 1 minute. Okay, now see these solutions are everybody. Yes, if equivalent capacitance between two opposite electrodes is farads, then what is CAB? See, actually, these are parallel plates. These are parallel plates arranged alternately, and we are looking at the cross-sectional view. Okay, not the cross-sectional view, side view. I will say side view. Actually, they look like thin plates, but these are parallel plates arranged one after the other as a sandwiched layer. Okay, na? Now to understand this problem, let us first polarize the material. See, like every body is electrically neutral. Electrically neutral means it is neither plus nor minus. Okay, like these plates, like let us say they are aluminum plates. These aluminum plates are electrically neutral. Now it is not polarized. Chalo, first to get capacitance, which is electrostatic property. First to get capacitance, which is electrostatic property, let us polarize the plates. Now, charge can neither be created nor destroyed, but you can separate them. You can polarize them. Now, that is the meaning. Now, suppose I give a very good DC voltage across this plus and minus, okay, between A and B. Then what happens, Nasser? Then what happens? Yes. Then what happens is all the plus ions in the battery acid, all the plus ions in the battery acid will attract the minus, will attract the minus ions of this A plate, okay, and remaining plus ions gets accumulated here. Remaining plus ions get accumulated here. That is number of plus equal to number of minus. We are neither creating charge nor destroying charge. Okay, only we are separating them. That is what happens. Then even in the negative side of the battery, all the negative ions of the battery acid will attract all the positive ions of the B plate. Okay, all the positive ions of the B plate, and remaining negative ions gets accumulated here, and remaining negative ions gets accumulated here. Again, we are only separating, but we are not creating charge, not destroying charge. Okay, that is the meaning of polarization. Okay, what is the meaning of polarization? Yes, what is the meaning of polarization? Please understand. Okay, this A plate, all minus will come here, plus will be there, and minus, all plus will come here and minus will be there. Okay, so we are polarizing the material. Okay, now we are polarizing the material. This is the meaning of polarization. Charge can neither be created nor destroyed. Now, once you polarize the material, now electric field will develop. Yes, electric field develop from plus to minus. So from plus to minus phase, this electric field develop. Here also plus to minus plate, electric field develop. Okay, here also plus to minus plate, electric field develop. Okay, that is the meaning. That is what happens. Now externally some leakage field will be that is called fringing effect. I am neglecting that. You may say, sir, what about the external plate? Yes, they may be there, but we are neglecting because that will be long distance, less field transfer. We neglect it. Okay, but yes, now electrostatic property came. Capacitor represents electrostatic property. Now we can model this as a capacitance. Now he said that the equivalent capacitance between two opposite electrodes. See, opposite electrodes means oppositely charged electrodes. Yes or no? Opposite electrodes means oppositely charged electrodes is C farad Z total. Yes or no? So in that regard, yes, in that regard, now I can say yes, between these two A and B, this is like 1C, and here also between A and B 1C, and here also between A and B 1C. But here A is positive, B is negative. Here also A is positive, B is negative. Here also A is positive, B is negative. Now in circuit 3 finally using lumped parameters. Yes, lumped parameters. Okay, like it is like node A, node B, again node A and node B. Okay, na? Yes, from A to B, there is capacitor of C with A positive. Again from A to B with capacitor of C with A positive. And again with A to B, capacitor of C with A positive. Okay, A positive. So this is now A, and this is now B. This is now A, and this is now B. Okay, now finally, how many nodes are there? Only two nodes. So finally, if I further simplify, this is A and this is B. Okay, so now this A to B, okay, 1C, okay, with A positive, okay, then similarly here also, okay, here also A to B with C, okay, with A positive, okay, that is also over. Then again A to B, yes, this is also capacitance C with A positive, okay. So we are analyzing between A and B. So all these are parallel concepts na. So CAB is 3C farads is the answer. See how physical system is being modeled here. So initially they are neutral. That means number of plus equal to number of minus. But by connecting a battery, current never flows through capacitor, but the charges get polarized. And that current in the directory, we call it as displacement current. It is not conventional current. I told you on the first day. Okay, first day itself I do. So because of the polarization, the charges get separate, and electric field property is it will start at plus charge and terminate at minus charge. Okay, it will start at plus charge and terminate at minus charge. Okay, due to which, yes, I can say yes. This is what happens here. Start at plus charge and terminate at minus charge. Okay, now that is what exactly happens. And now I can model this as parallel plate capacitor, and he gave that equivalent capacitance between two opposite electrodes. The opposite electrodes means oppositely charged electrodes. And now we got this as the answer. This is gate. What is CAB? This is also gate. What is CAB? This is total area A, and this is distance D. This is area A by 2. Here total area A. This is total distance D, but this is D by 2. And this is air. This is also air, but this green color one is dielectric with relative permittivity epsilon r. Relative permittivity epsilon r. Zero. So in the first case, he is inserting dielectric. Yes, in the first case, he is inserting dielectric to half the area but full distance. In the second case, he is inserting dielectric to full area but half distance. So in both cases, I need the capacitance CAB in terms of these parameters. Okay, quick. See, in the first case, I am inserting dielectric to half area but full distance. In the second case, I am inserting dielectric to full area but half distance. Now, in both cases, I need the total capacitance CAB. Quick, sir, everybody quick. Yes, time up. I want everyone to see now. Yes, time up, sir. Everybody see now. See, in the first case, he inserted dielectric to half area but full distance. Let us understand how this will work. Now see the concept. Suppose I give voltage across AB. as I told in the previous problem, like how this polarization takes place, like plus terminal of the battery where plus ions will attract all the minus ions of plate A and remaining plus will come. Here also all the minus ions of the battery inside acid will attract the plus ions of plate B and remaining minus will be coming at plate B. Like that, charge can neither be created nor destroyed, but you are only separating them. That process is called polarization. So here also when I give plus and minus, the plus ions of the battery will attract all the minus and remaining plus gets accumulated here. Remaining plus gets accumulated here. Let us say initially only air is there. Please, my explanation is, let us assume that only air is there initially. So all plus will come initially. Let us say this dielectric is not there. Let us say. Then here in the minus also, yes, all minus will come. Okay, all minus will come. Okay, let us say this is all minus is coming here. Okay, all minus. Okay, then what happens? Because here initially only air is there, the air particles also get polarized. Yes, initially because only air is there, only air particles get polarized. Yes, even then, yes, very low electric field gets established because of air, because density is low and permittivity is low, relative permittivity is low. Now by inserting dielectric to right side part, yes, half the area. Now in dielectric we have dipoles. We have dipoles. Now for the same applied voltage, because there are excess dipoles charges, the polarization is better. Due to which for the same applied voltage, this right side part, yes, where there are more dipoles forming, more charge gets accumulated. Left side air, less charge. Right side, more charge. Okay, because these dipoles also get polarized. So now what is happening for the same applied voltage? Where air is there, less charge is getting accumulated because the relative permittivity is low, one only. But where dielectric is there, relative permittivity is high. So permittivity is the ability to permit electric field lines. So here more strong electric field lines will come and more charge gets accumulated. Now I can model this as two capacitors. One is air capacitor, one is capacitor with dielectric. One is air capacitor, one is capacitor with dielectric. But in air capacitor, working voltage is same, but charge density is less. But in dielectric capacitor also working voltage is same, but charge density is different. Now it is like voltages are same, but charge density means initial displacement current. So it is like voltage equal, but current different. Voltage equal, but current different means parallel model of capacitor. Parallel model of capacitor. That is the final conclusion to explain all these things. Now, if it is a parallel model, then the CAB will be, okay, C1 plus C2. That is C of air, okay, plus C of dielectric. C of dielectric. C of dielectric. So what is C air? Epsilon naught. Okay. Epsilon R for air is 1. A is A by 2. A by 2 D. Okay. What about this dielectric material? Epsilon naught. Epsilon R. A is A by 2 D. So overall CAB will be, yes, epsilon naught A by 2D into 1 plus epsilon R. 1 plus epsilon R. Okay, that is the meaning. 1 plus epsilon R. Okay, now, so please understand this, sir. Yes, please understand this. Yes, please understand this. Okay, that is the answer. Now see right side, very interesting again. Same explanations are in the right side also. First let us assume I am giving plus voltage and minus voltage across AB. Okay, initially let us assume dielectric is not there, only air is there. Then all the plus ions of the battery will attract minus and remaining plus gets accumulated, but less charge as air density is low. And in the minus side also all minus will attract plus and remaining minus gets accumulated. But because initially I'm assuming air, that then the electric field intensity is low, okay, as very low electric field gets established. But now by inserting dielectric, to full area but half distance. Now full area but half distance, the overall dipoles have increased throughout the area. As overall dipoles have increased, more polarization for the same applied voltage, as more electric field gets established, due to which the overall charge density uniformly increases throughout the plates. Yes, throughout the plates. Okay, now I can model this as two capacitors where even air capacitor getting polarized and the dielectric part also getting polarized. But the charge density across the plates is uniform. Yes, the charge density across the plates is uniform. I can say the current is equal, the displacement current initially equal, but the working voltages are different. So here, as the charge density is uniform throughout the plates, Yes, the current is equal, but the working voltages are different. So this is like current equal, working voltage different means what is this model? Yes, this is like series model of capacitor. Series model. Now in series model capacitor, CAB is ulta. C1 C2 by C1 plus C2 na ulta to resistor formula. That is CA into C epsilon R. Okay, like that I'm writing C epsilon R by C1 plus C2. CA plus C epsilon R. Okay, so now in that regard, C1, C2, that is epsilon naught, epsilon R, okay, A by D by 2 into, yes, epsilon naught, epsilon R, A by D by 2 by C1 plus C2. That is epsilon naught A by D by 2 into 1 plus epsilon R. Now if you remove this, now if you remove this, okay, then I will say the CAB will be, yes, 2 epsilon naught epsilon R A by D into 1 plus epsilon R. 1 plus epsilon. This is the answer. This is the answer. Okay, now this is the answer. Okay, now, so please understand this. This is the answer. Okay, so that is very, very interesting, sir. Okay, so take your time to learn. Okay, that is very, very interesting concept we learn. Okay, that is about, yeah. Now I'm coming to another important problem. This is one front of you question here. Yes. Now the question is for the capacitive network shown. For the capacitive network shown, determine first A bit steady state voltages across each capacitor. B steady state charge accumulated by each capacitor. C energy stored in each capacitor. These are all in each capacitor. Okay, in each capacitor. Okay, na like that. In each capacitor. Then verify law of conservation of energy. Okay, and the last bit is verify law of conservation of charge. Law of conservation of charge. Okay, steady state voltage across each capacitor. Each capacitor. Steady state charge accumulated by each capacitor. Energy stored in each capacitor. Verify law of conservation of energy and verify law of conservation of charge. Okay, see, we did the same dual problem for inductor there. You remember currents, flux linkages, energy, law of conservation of energy, and law of conservation of flux. Here, steady state voltages, steady state charge, law of conservation of energy, and law of conservation of charge, like that. Okay, so now this is the circuit I'm giving. This is like 150 volt. Okay, 150 volt. This is 2 microfarad. This is 3 microfarad, 6 microfarad, 1 microfarad. Okay. Yes, 2 microfarad, 3 microfarad, 6 microfarad, 1 microfarad. Okay, now. Okay, chalo. Everybody, I'm giving you 2 minutes, try something. For the capacitive network shown, determine the steady state voltages across capacitors. Okay, charge stored on each capacitor, energy, verify law of conservation of energy and law of conservation of charge. This is 150 volts DC supply, sir. 2 micro, 1 micro, 3 micro, and 6 micro. Chalo, quick, everybody, do it fast. I'm giving you only 2 minutes, do it fast. Yes, everybody. Shall I listen now? Yes, everybody. See, here also initially what happens, imagine that you give sudden voltage. Now capacitors will never allow sudden change in voltage, but by closing switch you are giving sudden voltage. When sudden voltage is given to capacitors, impulse currents will flow. Impulse currents will flow, and then they will charge capacitor immediately, and then open circuit. So see, don't say directly that capacitors act as open circuit. Yes, capacitors act as open circuit for ideal DC in which state? A steady state. But what about the transient state? Like understanding. See, to understand example here, I am giving an extra example. Let us imagine that there is a DC 6 volts across two capacitors which are 1 farad and 2 farad, and I am closing the switch at t equal to 0. Now see, this is the logic to understand that problem. So imagine that I'm suddenly closing the switch. Then what current will flow? Impulse current delta of Ty. Capacitors will not allow sudden change in voltage. But if I give sudden voltage by closing the switch, impulse currents will flow. I told if you do allow sudden change, like impulse currents will flow. That impulse currents will flow for a negligible time and then they get charged. But in a series capacitor, now what is the argument? But in series capacitors, what must be same in steady state? Charges must be equal. Charges must be equal in steady state, not current. Because current flows in transient state. The moment I close the switch at t equal to 0 plus, current will flow. There is impulse current in negligible time. And once the capacitors get fully charged, charges must be equal. That means Q1 will be equal to Q2. But since Q equal to CV, yes, but since Q equal to CV, yes, since Q equal to CV, okay, here I can say C1 V1 equal to C2 V2. So here 1 farad into V1 equal to 2 farad into V2. That is equation 1. Also we know that V1 plus V2 equal to 6 volts. That is also true now. See, this V1 plus V2 should be 6 volts. Okay, now happily, if I solve them, okay, 3V2 equal to 6, so V2 equal to 2 volt, and automatically V1 equal to 4 volts. These are the answers. Now, if you check directly by voltage division rule, now listen, this is V1, this is V2 now. So if you take directly by voltage division rule, this V1 is in capacitor, voltage is inversely proportional to capacitance. This V1 is total voltage into opposite 2 by some 1 plus 2. So total it is 4 volts. 4 volts, see matching. Here also, if I say V2, voltage division rule, total voltage into opposite. Opposite is 1 by some 1 plus 2, 3. So this is again 2 volts, 2 volts, 2 volts. Okay. Yes. So directly voltage division, I would have said, but the concept exists in the transient state. Yes, the concept exists in the transient state that if I suddenly close the switch, impulse currents will flow. Yes, then impulse currents will flow for a negligible time. They completely charge the capacitors and then capacitors become open circuit. Okay. Now in an open circuited case, current cycle should not say, but charges must be equal. Charges are equal. And that is all. So the same phenomena here also, the moment I close the switch, immediately impulse currents will flow and capacitors charge and then they become open circuit. So now I can use the same idea here. Yes. First of all, yes. Now I will do voltage division rule. Now see, with that idea, now what is the voltage here? Let us see. First, this 3 and 6 series, 18 by 9 to 2 in parallel to 1, 3. So this is 3 micro, this is 2 micro. See, from here to here, it is like 3 microfarad. From here to here, it is 2 micro. Why? Because this I lumped it. Because 3 and 6 series, 18 by 9 to 2 plus 1, 3. So this voltage will be total voltage into opposite. Opposite is 3 micro by sum is 5 micro. Okay, that is nothing but 90 volts. Then remaining how much will come here? Out of 150, 90, so remaining 60 volts will come here. Yes or no? That remaining 60 volts will come here. Now that 60 volts again will be divided between these two capacitors which are in series. Yes, this voltage will be again total voltage 16 to opposite 6 micro by some 9 micro. Okay, so this will be obviously 40 volts. This is obviously 40 volts. Okay, and this remaining will be 20 volts. So the first bit we got, sir, the first bit, that is the steady state voltages. What are the steady state voltages? This is 90 volt, here 60 volt, here 40 volt, here 20 volt. Then charge also, steady state charge. Now charge across 2 microfarad, Q equal to CV, 180 microcoulomb. Now charge in 3 micro is also Q equal to CV, 120 microcoulomb. Now charge in 6 microfarad, 6 microfarad, Q equal to CV, that is also 120 microcoulomb. And finally, yes, finally, this charge on 1 micro, yes, will be Q equal to CV, that is 60 microcoulomb. 60 microcoulomb. Okay, so we get this is 180 microcoulomb, 120 microcoulomb, 120 microcoulomb, 60 microcoulomb. 60 micro. Okay, na? Yes, 60 microcoulomb. That is second bit also over. Now energy stored. Chalo, now directly go into energy stored. Okay, na? Energy stored. Okay. Now if I go to energy stored in 2 micro, that is half C VC square. Now what is the voltage across this? 90 square. 90 square. That is 8100 microjoules. Now energy stored in 1 micro, that is half C VC square, that is 60 square. Okay, that is nothing but 1800 microjoules. Now energy stored in 3 micro, that is half C VC square. Now what is in 340? That is 40 square. That is 2400 microjoules. Then energy stored in 6 micro, that is half C VC square. This is 20 square. Okay, that is 1200 microjoules. All these energies are in what form? All these energies are in what form? They are in electrostatic form, held up by the charge and the electric field. Okay, na? That is the meaning there. Now I'm going to the fourth bit. Okay, this is the third bit. This is the third bit. Now I'm going to the fourth bit. Okay, na? Fourth bit. That is law of conservation of energy. Law of conservation of energy. Yes, law of conservation of energy. Now here I have to prove that total energy delivered by the source is energy stored by the sinks, because pure capacitors, yes, pure capacitors will never convert and dissipate. They store and retain. So left hand side. So if I go to left hand side, energy delivered is equal to half C total V total square. Half into C total. Now what is C total? See, this is already 3 and 6 series. 18 by 9 to 2 plus 1, 3. But 3 is in series to 2. What is 3 is in series to 2? 3 is in series to 2 will become 6 by 5 microfarad into V total square. 180 square. Okay. 180 square. Okay. You check this. Yes, you check this. Okay. Someone should tell me this. Then right hand side also. Total energy stored. Total energy stored. Now add all these things, na, sir. We got this, na, sir. That is 8100 micro plus 1800 micro plus 2400 micro plus 1200 microjoules. 1200 microjoules. That many microjoules. Okay. You please do it. Okay. Someone can give me with your calculator. Anyone? See, 13500. Okay. Thank you, sir. 13500 microjoules. Please check this also. 13500 microjoules. If both left hand side is equal to right hand side, then okay. Then okay. Okay. That is the meaning. So please understand, sir. Pure capacitors will never convert or dissipate. They store and release. Okay, they store and release. Hence, I proved the total energy delivered. Yes, I proved that total energy delivered is total energy stored. Total energy delivered is total energy stored. And I got the answer same. Okay, that is wonderful. Now, fifth bit is very interesting. Law of conservation of charge. Yes, this is very interesting. So we have to prove total charge delivered. Okay, total charge delivered by the source, by polarizing the capacitors is the total charge accumulated by the sinks, okay, by getting polarized. Sinks are the capacitors. Okay, here total charge delivered by the source, okay, is equal to total charge accumulated by the sinks. Okay, total charge delivered by the source is the charge accumulated by the sinks. Okay, na? Total charge delivered by the source is the charge accumulated by the sinks. Okay, na? Chalo, now in that regard, if I observe, yes, total charge delivered is total charge accumulated by the sinks. Now left hand side, total charge delivered. Total charge delivered is, okay, C total into V total. What is C total? I simplified all now all together. Yeah, This is 6 and 3, 2, 2 plus 1, 3. 3 is in series to 2, na? The 3 is in series to 2 becomes 655 micro into V total. V total is 180. Okay, V total is 180. So overall you will get how much? C total into V total if you observe. Yes, if you observe, this is total 6/5 micro into 180. C total into V total. How much is V total? V total, V total is 150. Let me correct it. Yes, V total is 150, sir. Yes, thank you, thank you. One student told, chalo, V total is 150. Okay, now this is 180 micro coulomb. Thank you. Okay, so now what about the right hand side now? Total charge accumulated. Now this is very interesting. Now don't say here, sir, all charges I will add. No, sir, no, this is a single body we call. Don't say I will add all the charges and say total charge is 180 plus 120, 300, 420 and 480. No, don't say like that. Here I will say the total charge accumulated is the charge stored on one of the series capacitor to the source. Okay, one of the series capacitor to the source. One of the series capacitor to the source. Here total charge accumulated is a charge stored on one of the series capacitor to the source. Okay, is a charge stored on one of the series capacitor to the source. Now, which capacitor is in series to the source? 2 micro, 2 micro, which is 2 microfarad capacitor only, and that is Q accumulated is equal to 2 micro into, okay, C into V. What is the voltage there? Voltage is 90. That is voltage is 90. So this is also 180 microcoulomb. Hence I say yes, Q, okay, delivered is equal to Q accumulated. So law of conservation of charge is okay. So that is wonderful concept. Okay. Law of conservation of charge is a wonderful concept. Okay, please understand that is a wonderful concept. Okay. Everybody please understand. So why? See, I will explain the reasons. See, suppose if these are all registers, okay, if these are all registers and I want current in the circuit. If these are all registers and I want current in the circuit, okay. Yes, if these are all registers and I want current in the circuit, total voltage by total resistance is total current, right? Total voltage by total resistance is total current. There is also nothing but the current flowing in one of the series resistor to the source. Like that also, total charge means don't say I will add all this. Suppose imagine these are all registered like 2 ohm, 1 ohm, 3 ohm, 6 ohm. Will you add all the currents in 2 ohm, 1 ohm, 3 ohm and 6 ohm and say total current? No, na. So here also, total charge means don't say I will add all. It is also nothing but the charge accumulated by one of the series capacitor to the source. If they are resistors also, the current is nothing but the current flowing through the battery is nothing but the current flowing through these 2 ohms like that. Later what happens? Chalo, in series resistors current is equal but voltage will divide. In series resistors current is equal but voltage will divide. Yes or no? Current is equal, voltage will divide, and voltage division is proportional to resistance. But here in series capacitor, charge is equal, voltage will divide, and voltage division is inversely proportional to capacitance. In series capacitors, charge is equal but voltage will divide, and voltage division is inversely proportional to capacitance. Okay, then again you see now, okay, in parallel resistors voltage is same but currents will divide. In parallel resistor voltage is same but current will divide, and current division is inversely proportional to resistance. But here in parallel capacitors, this voltage is same. Yes, this is 60, this total is 60. In parallel capacitor, voltage is same, but charge will divide, and charge division is proportional to capacitance. Charge division is proportional to capacitance. This is 1 micro, this together is 2 micro. So out of 180, this together is 2 micro, na sir? Two-thirds will go here. That is 120. So out of 180, two-thirds will go here, 120. And out of 180, one-third will go here, 60. So that is how you should understand that. Don't say total charge means I will add all. Okay, total charge is a charge accumulated by one of the series capacitor to the source, which is 180 only. Hence, I prove that law of conservation of charge is also valid. Okay, now law of conservation of charge is also valid. That is very, very interesting, sir. Very, very interesting problem here. Okay, now. So that is how very interesting things that we learn. Now I am coming to outstanding problem, sir. Yes. Now, this is the question. Two capacitors of 1 farad, 2 farad are connected in series across 18 volts DC source. Two capacitors of 1 farad and 2 farad are connected in series across 18 volts DC source. Okay, determine their steady state voltages, charge, and energy. Okay, two capacitors of 1 farad, 2 farad are connected in series across 18 volts DC source, and determine their steady state voltages, charge, and energy. Now, if these two capacitors are disconnected from supply, okay, are disconnected from supply and connected with like polarities together, polarities together, okay, and connected with like polarities together, okay, then determine their steady state voltages, charge, okay, steady state voltages, charge, and energy stored in each. Okay, now if these two capacitors are disconnected from supply and connected with like polarities together, then determine their steady state voltages, charge, and energy stored in each. Okay, steady state voltages, charge, and energy stored in each. Okay, verify. Okay, law of conservation of charge and law of conservation of energy. Okay, verify law of conservation of energy before and after the change. It is a wonderful problem I want everyone to do. Two capacitors of 1 farad, 2 farad are connected in series across 18 volts DC source. Determine their steady state voltages, charge, and energy. Now, if these two capacitors are disconnected from supply and connected with like polarities together, then determine their steady state voltages, charge, and energy, and verify law of conservation of charge and law of conservation of energy before and after the change. Wonderful problems, sir. Like double inductor problem. Yesterday that was the first problem. Now this is the wonderful double capacitor problem. If you understand such ideal cases, na sir, then teaching practical things become more easy. Chalo, quick, everybody, quick. I'm giving you 2 minutes. Yes, I don't know how many did this, but the student who did this after the change, na sir, and you got correct answer. Wonderful, sir. It will be wonderful. Okay, chalo now, sir. He said that. Yes, he said that there are two capacitors. First, before change. Okay, let me write here. Before change. Before change. Okay, there is 18 volts DC source and 1 farad and 2 farad, both are in series. 1 farad, 2 farad. This is 18 volts. Now I want steady state voltages. Okay, what is this V1? V1 voltage division rule. Total voltage into opposite by sum. That is 12 volts. Then automatically, what is this V2? 6 volts. Steady state charge. Q1, C1, V1. That is 12 coulomb. Q2, that is also C2, V2, 12 coulomb. Okay, na? Then energy. E1 of C1. Okay, half C1, V1 square, 72 joules. Then E2 of C2, V2 square, 36 joules. 36 joules. Okay, that is also 36 joules. Okay, that is 36 joules. So now once you got it, now, yes. Now here, total energy is E1 plus E2. That you will get it as 108 joules. 108. And together connected, okay, together connected. Now together connected, okay, I am now writing here, together connected, then total charge is C total into V total. Total charge is C total into V total, that is 2 by 3 into 18, that is 12 coulomb only. Okay, so this is very, very interesting, sir. Together connected, yes, total charge is 12 only. Okay, but don't say 12 plus 12. I told you now such things like if two resistors are in series, don't say current in resistor 1, current in resistor 2 is total current. Current in one of them is total current. Like that here also two capacitors in series, charge in one of them is total charge. Okay, chalo. But sir, what he told then, now these two capacitors are disconnected from supply and connected with like polarities together. Now if you want to connect two capacitors like polarities, you have to separate them now. So to connect them, it is compulsory required to separate them. Okay. Once we separate capacitors, yes, once we separate capacitors, please understand. Yes, once we separate capacitors, then they are two independent isolated bodies or bodies. Then total charge is Q1 plus Q2. Now, once you separate them, this is valid argument. Q1 plus Q2, that is nothing but, yeah, 12 coulomb plus 12 coulomb. So now Q1 plus Q2 is 24 coulomb. This is equation A. Wonderful meanings are listen carefully. Sir, if they are connected together as a series, then total charge is only 12, sir. But the moment you separate, because we need to connect them with like polarities together by removing the source. You tell me if you want to connect like polarities means plus to plus and minus to minus. Separation is compulsory, na? Separation is compulsory, sir. So if separation is compulsory, then they become isolated bodies. And then when they are isolated bodies, total charge is, yes, Q1 plus Q2 is 24 coulomb. Okay. Total charge is Q1 plus Q2, 24 coulomb. Okay, na? Yes, 24 coulomb. Okay, na? Yes. Then what I will say, see, after understanding this, yes, Q1 plus Q2, 24 coulomb. Okay, na? Then what I will say, see, after showing this, then what I will say, okay, yes, now after showing like this, now, yes, after change, I'm connecting with like polarity together. What is the meaning? Now this is 1 farad and this is 2 farad. We are connecting with like polarities together, plus minus, we are connecting together. Now here, since parallel, okay, voltages are equal. V1 equal to V2. Okay, here V1 has to be equal to V2. Okay, na compulsory V1 has to be equal to V2. Okay, but since Q equal to CV, okay, that is Q1 by C1 equal to Q2 by C2. That implies yes, Q1 by 1 equal to Q2 by 2 farad. That implies Q2 is 2Q1. That is equation B. Now this is the trick, sir. This is a conclusion. Respecting law of conservation of charge only first. Okay, charge only. Okay, because there is total charge before is equal to total charge after. Then solve A and B. Now solve A and B equations, because before means the moment you are separating, change state means just before. See, connected together total charge is 12 only, but the moment you separate them, that is the before state now. Total charge is 24. So now solve equation A and equation B. Now we get what? Q2 is 2Q1. So total 3Q1 is 24. So Q1 is 8 coulomb. Q2 is 24 coulomb. Then voltages. Then V1 equal to V2. That is Q1 by C1. Na? Yes, Q1 by C1. Na? Yes, Q1. How much we got? 8 coulomb by C1. 1 farad equal to Q2, 16 coulomb by 2 farad, which is 8 volts only. Yes, 8 volts. Then energy E1 half C1 V1 square, 32 joules. Then energy stored in second capacitor half C2 V2 square, that is 64 joules. Now I will say here total energy is again E1 plus E2. Okay, first I will write like this. Now after change I will write like this. Now here total charge, okay, total charge is how much now? Q1 plus Q2, how much we are getting? Yes, that is total charge is 8 coulomb plus one is 16, sir. See, let me correct it. 3Q1 is 24, Q1 is 8C, but Q2 is 2 times, 16C. This is 16 coulomb. Let me correct it, because here I wrote correct. So 8 coulomb plus 16 coulomb, that is 24 coulomb. So here law of conservation of charge verified. Law of conservation of charge is okay, is verified. But what about energy total? Energy total is E1 plus E2. That is how much? 32 plus 64 joules, which is 96 joules. 96 joules only. But previously, how much is the energy? 108 joules. Now, how much is the energy? 96. So, law of conservation of energy has to be justified. Energy has to be justified. Okay. Now, before I write that, now mathematical proof. Yes, mathematical proof in S domain, Laplace domain. Very powerful, sir. Very powerful. Okay. Now, after change, what is going to happen? Now, capacitor with initial condition. See, capacitors with initial condition. Initial voltage across 1 farad is 12 volts and across 2 farad is 6 volts. So, initial voltage we have to take. So, this is V0 by S, 1 by CS. This is how much now? 12 volts. 12 by S and 1 by CS. 1 by S ohms. And this is also V0 by S. V0 by S. What is V0 by S? What is V0 now? Yes, what is V0? Yes, this is 12. Okay, now this is 12. Initially, see, let me correct. This is 12 volts and this is 6 volts. Okay, so this is 6 by S, 1 by CS, 1 by 2S. Okay, both are parallel. Yes, both are parallel. And now I need nodal. If I do, yes, this is our total V of S. Okay, this is our total V of S. Okay, now if I write nodal equation, okay, KCL. Okay, V of S minus 12 by S whole by 1 by S plus V of S minus 6 by S whole by 1 by 2S equal to 0. So V of S into this is S plus 2S is equal to 12 plus 12, 24. That means V of S is 24 by 3S, 8 by S. So V of T is Laplace, inverse Laplace of V of S, which is 8 volts, which is equal to V1 equal to V2, which we got same, na sir? We got same, na sir? See, we got same. That is wonderful. So, conclusion. Here, yes, the same way. Here, some part of, because law of conservation of charge is different, but here, some part of energy from previous state has been utilized to redistribute the flux, redistribute the charge among capacitors to maintain equal voltages. Wonderful concept. Some part of the energy. Why? Because initially total energy is 108 joules. Okay. Then after that we got total energy how much? 96 joules. That means 12 joules is missing. But I'm not saying we are violating. Some part of the energy from the previous state has been utilized to redistribute the charge among capacitors to maintain equal voltages. Everyone think about this problem again. Everybody think. Initially, when they are connected together, total charge is 12 only. But the moment we separate to reconnect them back with like polarities, then total charge is this. That is a very important trick here. In inductors, that was not the case, sir, because they are initially isolated bodies. That was the difference here. Then, yes, after change, but taking law of conservation of charge, and the proof came here, sir. This concept I will teach you in Laplace. See, some students who are not understanding how to write capacitors with initial condition, this part I will teach you later. Don't worry. But once you get that proof, mathematically, I am also proving that voltages should be 8 volts. And that voltages 8 volts came only when you take law of conservation of charge. But that does not mean that we are violating law of conservation of energy. We say some of the energy has been utilized to redistribute the charge among capacitors. Okay, and that is the meaning there. I'm going to another interesting problem, sir. If V of 0 is 0 volts, that means there is no initial condition. Plot the voltage across 1 farad capacitor, 1 farad capacitor. Okay, plot the voltage across 1 farad capacitor. If current through it is as shown below. If current through it is as shown below. So I'm giving only 1 minute. Okay. Yes, please understand here. If V of 0 is 0 volts, plot the voltage across 1 farad capacitor if current through it is as shown below. Okay. If current through it is as shown below. Okay. If V of 0 is 0 volts, plot the voltage across 1 farad capacitor if current through it is as shown below. Okay. If V of 0 is 0 volts, plot the voltage across 1 farad capacitor if current through it is as shown below. Chalo, 1 minute, try something. If V of 0 is 0 volts, plot the voltage across 1 farad capacitor if current through it is as shown below. Okay, everybody, see, if V of 0 is 0 volts, plot the voltage across 1 farad capacitor if current through it is as given. Now, sir, this time he is giving current and again he is plotting voltage. In inductor, what happened? V is L di by dt. But in capacitor, V is 1 by C integral I dt. This is an integration function. Yes, in capacitor, V is 1 by C integral I dt. But if you expand this from minus infinity to t, we will write this as 1 by C integral minus infinity to 0 I dt plus 1 by C integral 0 to t I dt. But this is called as initial condition. This is called as initial condition. So now I will write this as V of t is V of 0 plus 1 by C integral 0 to t current function dt. Current function V of t equal to V of 0 plus 1 by C integral 0 to t current function dt. Okay. Now this is a DC current, but it is not ideal DC. It is a pulse. You can say it is a rippled DC. Increasing, decreasing, increasing. Actually, it is a triangular waveform, but unidirectional. Current is increasing, decreasing in same side, same direction. So it is DC current only, but rippled DC. So let us do piecewise linearization. What is piecewise linearization? As I told you, sir, 0 to 1, 1 to 2, 2 to 3, like that we will do. So first from 0 to 1 second if I go. Yes, 0 to 1 second if I go. Yes, this V of t is V of 0 plus 1 by C. C is 1 farad na integral 0 to 1 current function dt. So what is current function from 0 to 1? Current function from 0 to 1 is y equal to mx. Slope is opposite by adjacent. See, opposite by adjacent. How much is opposite by adjacent? 1 only. T dt. Now V of 0, he gave 0. He gave in the question initially there is no charge. V of 0, 0 plus this is t square by 2, t square by 2. And what are the limits? Limits are from 0 to 1. Now how to read this integration function? At t equal to 0, V is 0. At t equal to 1 second, at t equal to 0, V equal to 0. At t equal to 1 second, V is half volt. V is half volt, but it is going like what function? T square by 2. Parabolic function. Parabolic function. It is going like parabolic function. Okay, it is going like parabolic function. Then if I go from 1 to 2, let me plot this. Okay, chalo. It is going like parabolic. Now see, correspondingly I will plot here. Everybody watch this. I am plotting the voltage. Voltage, okay? Voltage across capacitor. Chalo, now what is that we concluded? It is an integration function. Shape is t square by 2, limits are 0 to 1. At t equal to 0, V is 0, but at t equal to 1 second, it reaches half volt, but like a parabolic. T square by 2, na sir? Yes, this is the shape. Chalo, it reaches here and goes this way. It reaches how much, sir? It reaches how much? It reaches half. Chalo, it reaches half. It reaches half. Okay, na? Half. Okay, so now let us go from 1 to 2. Let us go from 1 to 2. Okay, let us go from 1 to 2. V of t equal to, again, V of 0 plus 1 by C integral 1 to 2 current function dt. Now what is the current function? Now if you take here 2-point formula, yes, here 2-point formula, this point is like 2 comma 0 and this point is like 1 comma 1. Like y minus y1 is equal to m y2 minus y1 by x2 minus x1 into x minus x1. Y-axis is current axis, I. Slope is minus 1, minus t plus 2 will come. Okay, this you do it again, minus t plus 2. So this is minus t plus 2 will come. Minus t plus 2 dt. Now, what is V of 0 now? Previous state. Previous state is already reached half volt. And this is minus t square by 2 plus 2t. Okay. Yes, minus t square by 2 plus 2. And what are the limits here? Limits. This is from 1 to 2. This is also from 1 to 2. Now I can say t equal to 1 second. V is half volt. At t equal to 1 second, V is half volt. But at t equal to 2 seconds, V reaches how much now? Integrate, sir. If you integrate half minus half t square, 4 minus 1 plus 2 into 1. So this is 2 and a half, 5 by 2 minus 3 by 2. See, 5 by 2 minus 3 by 2 is how much, sir? 1 volt. 2.5 minus 1.5 is 1 volt. You integrate now. Integrate with limits. It reaches 1 volt. But again, what is the shape of the function? This function is like ax square plus bx plus c. It is also parabolic. Parabolic. Yes or no? It is also parabolic. So, yes, now if you show, it reaches from half volt. See here, it reaches from half volt to 1 volt in a parabolic shape. Okay. So, half volt to now 1 volt it will reach. 1 volt, but it will reach in a parabolic shape. Parabolic shape. Initially it went like this. Now it is going like this. Okay, let me write neatly. You may say, sir, how can you decide the shape? See, t square by 2 everyone can expect. First t square by 2 everyone can expect because at t equal to 0, 0, at t equal to 1, half, at t equal to 2, 2, at t equal to 4, 3, it is 4.5, at t equal to 4, it is 8, like that it shoots up like. So that shape everyone understood. But what about this shape? What about this shape? Everyone will doubt. Now, if you doubt that shape, let us take a sample point. Let us take a sample point. Sample point. Now listen carefully. Let us find v at t equal to 1.5 seconds. Okay, but here to integrate, that is 1 by 2 minus t square by 2. Okay, plus 2t. But you have to integrate from where to where? 1 to 1.5. 1 to 1.5. That becomes half minus half. 1.5, 2.25 minus 1. Okay, plus 2 into half. So overall it becomes 1.5 minus, this is 1.25 by 2, 0.675. So overall 0.875 volts will come. Now imagine, sir, imagine. That means, see, if I draw a straight line here, linear, then at 1.5, how much would have been the voltage if it was a linear function? If it was a linear function at 1.5 seconds, voltage should be exactly middle, somewhere 0.75 should be there, na? At 1.5 second, if it was a linear function, if it was a straight line function, at 1.5 second, voltage would have been 0.75 volts. But here at 1.5 seconds, we got how much? 0.875 volts. So it will bulge like this. If it is less than 0.75, it would have come like this. If it is less than 0.75, it would have come like this. If it is now, it is greater than 0.75. So that is how in exam, if you are getting any doubt, na sir, take some random point and argue. Okay, take some random point and argue. Okay, na? So that is how I argue the shape in this case. Okay, then just for sample, I will take one more point, one more time, like from 2 to 3 seconds. Chalo, from 2 to 3 seconds, v of t equal to v of 0 plus 1 by c integral 2 to 3. Okay, current function. But what is the current function now? Now this point is like 3, 1. Again, x1, y1, x2, y2. Y minus y1 is slope m, y2 minus y1 by x2 minus x1 into x minus x1. So the slope is again 1. T minus 2 will come. Yes, t minus 2 is the thing with intercept. Okay, t minus 2. So if I do, this again becomes t minus 2 dt. So here again, what is v of 0 now? Previously it already reached how much? 1 volt. Na? So 1 plus t square by 2 minus 2t. And limits are what? 2 to 3 and 2 to 3. Now you can say, yes, at t equal to 2 seconds, v was at 1 volt. Now at t equal to 3 seconds, what is v now? Integrate 1 plus half plus 3 square 9 minus 2 square 4 minus 2. So minus 1 plus 5 by 2. 2.5 minus 1, 2.5 minus 1 is 1.5 volts, 1.5 volts. Again, what is the nature? What is the nature? Yes, you see the nature. Ax square plus bx plus c. This is also parabolic. 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 Yes or no? Parabolic shape. Yes, parabolic shape. So again, you can say yes. Yes, where it will go? It will reach now 1.5 volts. Okay, 1.5 volts. Okay, 3 by 2 volts, but in a parabolic shape. Parabolic shape. Now you can continue, sir. Again, it will go like this. Again, it will go like this. That continues. Okay, that is the answer. Okay, now that is the answer. So the wonderful problem, sir. Yes. But integration function, take your time to learn. Okay, now there is a wonderful problem. So I'm going to the next question, sir. This is a wonderful gate 2 marks question. Plot current I of t if voltage V of t is given as Okay. Now this is the first circuit he gave. This is the circuit he gave. This is V of t, 1 ohm, 1 farad. I need this I of t. Plot current I of t, voltage V of t. Now voltage function is giving here. Chalo. Plot current I of t. See all the students who are raising hand. Once I give break at 9:30, not break. I am going to close a little early. I told her. Then you ask doubts, na sir. You ask doubts. Okay, then I will argue anything with you and I will explain everything. So you have to understand. Take time. If I take individual doubts of 300 students here, it is not possible like that. Please understand and try to accept that request. If it is a class, na sir, then everyone would be seeing, everyone would be understanding. Your discussion could be general discussion, and everyone may understand. Now here, what happens in this offline, online? What you and me are talking, others won't understand also. So everybody, plot current I of t if voltage V of t is given as this. Chalo. Okay. 1 minute I'm giving just predict the shape. Now this is a bipolar voltage, AC voltage. Okay. Bipolar voltage, AC voltage. Okay. Now predict the shape here. Plot current I of t if voltage V of t is given here. Okay. Plot current I of t if voltage V of t is given. Okay, everybody, now see here. Now he's asking us to plot total current. Okay, he's asking us to plot total current. Okay, but he gave a voltage which is symmetrical triangle. I told Nasser today I'm giving early, leaving early. There is no breakfast. Drink break. What drink you want? Please understand, sir. Okay, please understand. Chalo. Now see here. Yes, one student wrote correct answer. Ramp plus step. Ramp plus step. Okay, chalo. Now I will leave a little early, sir. I told I need to go to vaccination and something very important. I told Nasser. Please understand that. Okay. Now see here. Plot current if voltage function is given like this. Now see, you are giving voltage across parallel RC circuit. So if you can first understand IR and IC, then I will apply Kirchhoff current law. So here Kirchhoff current law we are doing, but Kirchhoff current law for which signals? Time varying signals, where total current I of t is IR plus IC. Chalo, first let us plot IR and IC. First I will plot IR here. Okay, everybody, first I will plot IR. Okay, yes, if I plot IR, okay, IR of t. Now here resistance is clearly 1 ohm. Resistance clearly 1 ohm. When this voltage is given across 1 ohm, same current will come, where positive peak will be 1 volt by 1 ohm plus 1 ampere. Negative peak will be minus 1 by minus 1 by 1 minus 1 ampere. So ditto will come. So ditto will come. Yes, it will be same. It will be same. Same. So it is plus 1 ampere minus 1 ampere. Okay, this is like half 1, 3 by 2, 2 and 5 by 2. This is ditto. This is ditto. But what about current through capacitor? Now IC is C dV by dt. That is different now in capacitor. So let us plot even capacitor current. Okay. Yes, let us also plot capacitor current. Let us plot capacitor current. Now here I'm talking about current through capacitor where I is C dV by dt. Okay, I is C dV by dt. Okay, so first resistor is a homogeneous proportional element. There is no confusion. I is V by R, so same shape will come there. But when it comes to capacitor, I is C dV by dt. Let us do again piecewise linearization. Now listen. See here, luckily because it is a differentiation function, I need not have any intercept. So first from 0 to half second. So from 0 to half second, this IC will be C. C is how much? 1 farad. Okay, d by dt of V. What is voltage function? See, what is the voltage from 0 to half? 0 to half. What is the voltage function? See, y equal to mx. Slope is opposite by adjacent. See, opposite is 1, adjacent is half. Opposite is 1 by adjacent. 1 by 1 by 2 is 2. That is nothing but 2t. Yes or no? 2t. So it is plus 2 ampere step. Plus 2 ampere step. Okay. So it will come as plus 2 ampere step. 2 ampere step. Now let us directly go. See now this voltage function slope is same from half to 3 by 2 na, same negative slope na. So directly from half to 3 by 2 if I go, again IC is C is 1 d by dt of voltage function. But here intercept luckily I don't want, sir, because we are differentiating. However, in integration function intercept is important. But in differentiation function, differentiation of constant is 0. Na? But what is the negative slope? Opposite 1 by adjacent 1 by 2. So minus 2t plus some intercept. Okay. This will be minus 2t plus some intercept C1. But this is minus 2 ampere step. Minus 2 ampere step. This is minus 2 ampere step. This is like minus 2 ampere step. Minus 2 ampere step. Okay. Then if I go from 3 by 2 to 5 by 2, okay, IC is C, d by dt of, now again sir, it is positive slope. Again slope is how much? Opposite 1 by adjacent, which is again half. Yes or no? 2.5 minus 2, half. So it is plus 2t some intercept, plus 2t minus some intercept C2. But differentiation of constant is 0, plus 2 ampere step. Chalo, plus 2 ampere step. So again it is plus 2 ampere step. Plus 2 ampere step. Okay, plus 2 ampere step. Okay, then again minus 2 ampere will come, and again plus 2 ampere will come. Like that it will go, sir. Chalo, wonderful, sir. Okay, now this is a combination of yes, ramp and step. One student gave correct answer, sir. Very good. One student I saw just now. Yes, one student gave. Yes, Gopal gave correct. Okay, Gopal gave correct. So now in that regard, everybody. Now let us add these two. Now Kirchhoff current law. Now let us also plot the actual question. Okay, he's asking voltage. Yes, let us plot this. Okay, let us plot the actual total current, which is Kirchhoff current law between two currents. Okay, which is Kirchhoff current. I mean seconds. Okay, this is the total current I am taking, which is sum of these two currents. Okay, this is however half second, 1, 1.5, 2, 2.5, 3, like that it goes. It goes for. Okay, 0, half, 1, 1.5 to 2.5. So now in that regard, yes, now in that regard, if I add, yes, now in that regard, if I add everybody, chalo, in that regard, if I add now, very carefully, if I add everybody, now what is going to happen now if I add like that? Yes, if I add like that, what is going to happen? Now see here. Now see, register current is very simple to understand. But what about the capacitor current? Capacitor current is stochastic. It is discontinuous because at half second and at 1.5, 3 by 2 and at 2.5, 5 by 2, you cannot define this function. See, when it is vertically falling suddenly in 0 time, we cannot define this function. That is why we call this as stochastic or discontinuous function. In such case, what you do, take limits and apply KCL. Okay, take limits and apply KCL. What is that limit? See, first of all, at t equal to 0, IR is 0, but IC is 2. Okay, na? At t equal to 0, IR is 0, IC is 2. Okay, na? So total it will become 2 na. So this is like 1 ampere, this is like plus 2 ampere, and this is like plus 3 ampere. Negative side it is minus 1 ampere, minus 2 ampere, minus 3 ampere. Okay, so yes, if you observe that at t equal to 0, IR is 0, IC is plus 2. Overall it becomes plus 2. Okay, then at t equal to half, you cannot define IC. So what you do, take limits, half minus half plus. What is the meaning of half minus? Just before half. What is the meaning of half plus? Just after half. So half minus IC is 2 and IR is 1. Total it will become 3. Yes, this will be a trapezoidal function like this. Then go to half plus. Half plus means just after half. Why I'm applying limits? The reason I'm applying limits because this current through capacitor is stochastic, discontinuous. So if I go half plus, IR is still 1, but IC is minus 2. IR is still 1, but IC is minus 2. So 1 minus 2 is minus 1. So it will suddenly jump to minus 1. Okay, it will be suddenly jumping to minus 1. It's minus 1. Okay, then at 1, no confusion, sir. At 1, this is 0, this is minus 2, overall minus 2. At 1, it is minus 2. Then at 3 by 2 minus 3 by 2 plus 3 by 2 minus, this is minus 1, minus 2, overall minus 3. Minus 1 minus 2 overall minus 3. Minus 1 minus 2 overall minus 3. Minus. And at 3 by 2 plus 3 by 2 plus 2, see 3 by 2 plus means just after 3 by 2. This is still minus 1, this is plus 2. Minus 1 plus 2 is plus 1. It will go plus 1. See, until here it will plus 1. Okay. Then at 2, this is 2, this is 0. Overall it reaches 2. Overall it reaches 2. See, 2 is 8. Overall it reaches 2. So this is for one cycle. See, for one cycle of supply voltage, one cycle of current is like this. Now continue from there, sir. So again, what happens now, sir? It will go from 2 to 3, 3 to minus 1. Okay, na? Minus 1 to minus 3, minus 3 to plus 1. Okay, minus 3 to plus 1. Go minus 3, minus 3 to plus 1, plus 1 to plus 3, like that it goes. That is the meaning. So this is the correct shape. Now, such understanding, if you get sir, later in pulse and digital circuits, power electronics, so many other subjects, sir, you can easily understand. You can easily understand. Yeah? You can easily understand how they are behaving. Okay, that is the meaning there. Okay, you can easily understand how they are behaving. Okay, that is the meaning here. Okay, so simple, sir. I applied KCL, but why I took limits here? Because this current of through capacitor is not a continuous function; it is discontinuous function. Okay, that is important. Now I'm asking another question here. Everybody, yes, this is the question. Three capacitors of dissimilar rating, dissimilar. Okay, dissimilar rating. Okay, or ratings are connected as a network shown. Are connected as a network shown. Okay, three capacitors of dissimilar ratings are connected as a network shown. Okay, the voltages across them indicate their ratings. Or breakdown level. What is the overall maximum safe voltage? What is the overall maximum safe voltage? What is the overall maximum safe voltage without breakdown of any capacitor? Okay, what is the overall maximum safe voltage without breakdown of any capacitor? And also determine the total. Okay, I will say overall determine. Okay, and also determine the maximum storage charge. Maximum stored charge in network. Okay, three capacitors of dissimilar rating are connected as a network shown. The voltage across them indicate their breakdown level. What is the overall maximum safe voltage without breakdown of any capacitor, and also determine the maximum stored charge in the network. Okay, then I'm giving the circuit here. Okay, I'm giving the circuit here or network. Two microfarad, 2 volt, 3 microfarad, 3 volt, 5 microfarad, 5 volt. Okay, there are three capacitors. Now read the question. There are three capacitors of dissimilar rating. Okay, are connected as the network shown. The voltages across them indicate their breakdown level. That means this capacitor, if you exceed 2 volts, it will break. This capacitor, if you exceed 3 volts, it will break. This capacitor, if you exceed 5 volts, it will break. But what is the overall maximum safe voltage? What is the overall maximum safe voltage without breakdown of any capacitor? What is the overall maximum safe voltage without breakdown of any capacitor? Okay, what is the overall maximum safe voltage without breakdown of any capacitor, and also determine the maximum stored charge in the network. And also determine the maximum stored charge in the network. So I'm giving you 2 minutes, write something. Okay, now see, this is a very interesting problem on dissimilar ratings. See, never we go with such problems. Now see, he is asking what is the overall maximum safe voltage. Now, chalo, let us assume that I am giving overall Vmax. I want to know this maximum value without breakdown of any capacitor. Okay, so let us compare each capacitor separately because this is dissimilar rating now, sir. Yes, because this is dissimilar rating, let us compare each capacitor separately. First, let us compare 5 microfarad. So for 5 microfarad capacitor, because directly it is in parallel, Vmax is 5 volts. Vmax is 5 volts. That is the first answer. Let us go to 3 microfarad capacitor. Now in 3 microfarad capacitor, both are in series now. Both are in series. Voltages will divide. This voltage will be total voltage into opposite by sum, but that voltage should not exceed its rating. Nah, that rating is how much? 3 volts. So total voltage into opposite 2 micro by sum 3 plus 2 5 micro, but that should not exceed the 3 volts. So this will be now with respect to 3 micro, Vmax will be how much then? That is 15 by 2, 17.5 volts. That is second possible answer. Now let us come to 2 microfarad capacitor. Now here also these two are in series. This voltage will divide between these two, but it should not exceed its rating 2 volts. So again voltage division rule in capacitor. This total voltage into opposite 3 micro by sum 3 plus 2 5 micro. Again it should not exceed its rating 2 volts. Okay, that is again Vmax allowed is only 10 by 3, which is 3.33 volts. Now what is the overall maximum safe voltage? Now conclusions are, see, based on different capacitor ratings, we got different answers. But overall maximum safe is only the least one. Overall maximum safe is the least one. So I say the overall safe is only how much? 10 by 3 volt. That is 3.33 volt. Because if you give 5 volt, this 2 micro will blast. If I give 7.5 volt, these two will blast. But if I give 3.33 only, everyone will survive. Because the moment I give 3.33 here, this will automatically reach 2 volts and there is a maximum limit. If you exceed that, this will blast. So that is how the answer is this. Then Qmax. Now Qmax also is asking maximum storage charge. That is C total into Vmax. Vmax. C total is how much? Now see, these two are in series. Okay, that is 6 by 5 plus 5 micro. That is 6 by 5 plus 5 microfarad into Vmax 10 by 3. So this is nothing but 31 by 5 into 10 by 3 microcoulomb. That is nothing but 62 by 3 microcoulomb. 62 by 3 micro. 62 by 3 microcoulomb is what is Qmax. Okay, that also is done. And that also is done. Okay, now. So now I am giving an interesting question. IAS objective. This is similar rating. How many capacitors of 200 volt 2 microfarad are required to be connected okay, how many capacitors of 200 volts 2 microfarad are required to be connected to work at a system voltage okay, system level of, I will write system level of 600 volts 4 microfarad. This is very interesting. All are similar rating. Previous problem is what? Dissimilar rating capacitors. But here all are similar rated. So how many capacitors of each rated 200 volts 2 microfarad? Okay, how many capacitors of each rated 200 volts 2 microfarad are required to be connected to work at a system level of 600 volts 4 microfarad? Chalo, 1 minute only. 1 minute, sir. You can tell the answer in no time. How many capacitors of each rated, okay, 200 volts 2 microfarad are required to be connected to work at a system voltage of system level of 600 volts 4 microfarad? So 1 minute, sir. Very easy. So many are giving answers, sir. Very good. So many are giving answers. Chalo, 1 minute only for this problem. How many capacitors of each rated 200 volts 2 microfarad are required to be connected to work at a system level of 600 volts 4 microfarads? Okay, everybody now see here. See, these are all similar capacitors, sir. See, how can you improve the voltage rating? Yes, you can improve the voltage rating by connecting them in series. Suppose this is 2 microfarad, 200 volts, 2 microfarad, 200 volts, 2 microfarad, 200 volts. So total it will now block how much? 600 volts. That is good, sir. So series capacitors will block more voltage. Like series batteries will give more voltage. Series diodes will block more voltage. Like series capacitors also will block more voltage. That is very good. But now because this is 2 microfarad, 2 microfarad, 2 microfarad, overall this has become 2 by 3 microfarad. But I need total how much? 4 micro. Then what I will do? I will connect one more such series branch. Okay, like this is also becoming now 2 microfarad, 2 microfarad, 2 microfarad. So overall it will block now again 600 volts, but again this becomes another 2 by 3. So 2 by 3, 2 by 3 become 4 by 3. So my challenge is I will connect such n such things. Okay, n such parallel branches. Okay, I will connect now, yes, n such parallel branches where each branch is offering 2 by 3 microfarad, so that I should reach total 4 microfarad. Yes or no? So that will be now how many parallel I require? That is 6 parallel branches. But in each branch, how many are there? 3. I need 6 parallel branches. And in each branch there are 3. So total is 6 into 3, 18 capacitors. 18 capacitors is answer. See, like 3, 3, 3, 3, 6 times, sir. Because each branch will block 600 volts, but each branch is offering only 2 by 3. Like 2 by 3 into 6, if you take 4 micro will come. So total 18 capacitors. Now, sir, for what value? This is gate bit. For what value of R? Energy stored in inductor and capacitor are equal in steady state. Okay, for what value of resistance are energy stored in inductor and capacitor are equal in steady state. What value of resistance are energy stored in inductor and capacitor are equal in steady state. So it is which steady state? DC steady state. Now, 1 minute. For what value of resistance are energy stored in inductor and capacitor are equal in steady state. For what value of resistance are energy stored in inductor and capacitor are equal in steady state. Okay, chalo sir, I'm going now. See here in DC steady state, you know, inductor acts like short, capacitor acts like open. Okay, inductor short, capacitor open. Okay, na this inductor is short, capacitor is open. Now, if I know the current through inductor IL and if I know voltage across capacitor VC, I can equate their energies. But here, because capacitor is open, inductor is short, these 2 and R become parallel now. So this current will be total current into opposite 2 by sum is 2 plus R. So overall current will be 10 by 2 plus R. Then what is this overall voltage? V equal to IR. This VC will be IL into R only. That is nothing but IL into R is 10R by 2 plus R. 10R by 2 plus R. Okay, that will be 10R by 2 plus R. Okay, now that is nothing but VC. This is IL. Now he said both energies are equal. That is energy in capacitor is equal to energy in inductor. But however, in steady state, half C VC square is equal to half L IL square. Okay, remove this half. C is how much? 160 micro. VC square. Now VC square is this na 10 square R square by 2 plus R whole square. Okay, and L is how much? 4 milli into IL square. That is nothing but 10 square by 2 plus R whole square. Now if you remove, yes, remove these two. Just remove these two. Okay, and 4 ones are here, 440s are. So R square is 1 milli by 40 micro is nothing but kilo by 40. Milli by micro is kilo now. Kilo means 1000 by 40 is 25. When R square is 25, R is 5 ohms. R is 5 ohms. R is 5 ohms. Okay, chalo sir, with this inductor capacitor chapter is perfectly done. Now see, today, see everybody, see I'm giving my WhatsApp number. Everybody listen, don't raise your hand. What I'm trying to say is, see my WhatsApp number. Okay, WhatsApp number is 9000616124. So today's class doubts also you post there. I'm going to post your notes now because I'm little hurry, sir, because there 11 o'clock I have to read that Sanat Nagar, sir, which is at least 17 kilometers from here. So again, that government agency, sir, there is a problem. So yes, everybody, see my WhatsApp number is 9000616124. Today's doubts also you post there. Sir, I am deep, I'm so and so today's Vicom class student. Please explain this problem. I will call you, sir. I will call you afternoon. Afternoon after 2 o'clock, 3 o'clock, I will call you and we will have a discussion. Okay, na? So please excuse me today. Please everyone note down my WhatsApp number. After completion of syllabus, I will share a lot of material also. But today's doubts, you please post it here. I will call you back. So 9000616124 is my WhatsApp number. Everyone noted down. Please raise your hand. Did you note down? Please note down. This is my name is Krishna Verma. Okay, Krishna Verma, network faculty. BS Krishna Verma. I am in AS since 2009, sir. Okay. So yes, 9000616124. BS Krishna Verma, network faculty. So what you do, today's doubts, everybody, please post it here. I will call you back in the afternoon because there is no time, sir. I'm leaving. Even that capacitor problems, whatever doubt. Now think again. See, do again, think again. Wherever doubt you are getting, that slide you post to me. In that WhatsApp, you post that slide which I'm sharing you now. Then I will talk to you and we will have a elaborated explanation. Okay, everybody, is it okay? Is it okay? Okay, na sir, that I will do. Okay, so everyone note down my WhatsApp number and I will call you. Okay. Okay, I am Krishna Verma, faculty in ACE Academy. Okay, chalo sir, I am leaving today, but I will talk to doubts and also after completing the syllabus in few more days, I will share everything. Tomorrow it is from 7 to 1, sir. Tomorrow 7 to 1. Please remember, tomorrow 7 to 1.